I think I said at the end of the last clip that we were going to be doing the integral test for series, and I just got a little bit ahead of myself. So the rest of this particular section is devoted to various ways that we can tell. So as we saw, sometimes we can really kind of get a sense as we look at a graph of partial sums or a table of the partial sums, we can get a sense that the partial sums are approaching some limit. But a lot of times it's not really clear what's going on with the partial sums. So there's a number of techniques for examining series and just determining whether or not they converge. Once you know that a series converges, then determining the limit is another story. And it actually turns out that having formulas for the actual limit of a series it's pretty rare. And so in fact, the geometric series is really the only one that I could give you off the top of my head where there's a fast and easy formula for the actual limit of the series. But in many cases, it's enough just to know that the series converges, and then we can use other techniques to estimate the limit once we know that the series is in fact convergent. So our first test is the divergence test, and in fact, this test is kind of motivated by this observation that we made in the graph here. So unfortunately, I'm not sure that this was saved over here. Okay, I'm afraid it wasn't saved. But when we went through and graphed, okay, so here again, things have been reset, but at least we're starting at 1 over x. So I'm going to go ahead and just put in here x over x plus 1. And so if you remember here, in this particular series, as we kept going out, we noticed that this series diverges because the sequence of partial sums, which is here in red, is shooting off, and in fact, as you look at successive red dots here, they differ by approximately 1 as you get far enough to the right in the graph, and that's because the black x's, so the terms, are getting closer and closer to 1. And so the idea is that if there's going to be any hope, right? So here's the idea. So if there's going to be any hope of a series converging, the terms must go to 0. Okay, and so let me go ahead and add a little notation here. So if we say that our series is the sum of bk, right? I think in your textbook they use ak, so k equals 1 to infinity. Then the terms bk have to go to 0. In other words, the limit as k goes to infinity of bk must be equal to 0, right? And the reasoning here is exactly as I kind of showed on the previous screen, is that, okay, so here, if the sum, so say the sum of bk, say this is equal to some limit L, right? Then the idea is, then we must have, okay, if these are the partial sums, right? If we're going to be having these SNs staying close to L, then if they have to stay arbitrarily close to L, then they can't be oscillating a lot. So SNs can't oscillate. And in fact, so because the SNs can't oscillate by a lot, well, how much does SN differ from SN plus 1? It differs by the n plus first term in the series. So, so here, right, how much the purple dots are changing, those partial sums are changing, is corresponds to the size of the terms, the individual terms of the series that are being added up. So sometimes I call the sequence of terms also the sequence of sum ends, because I think it's more descriptive, but your book uses the word terms here. So the SNs can't oscillate by a lot. The terms Bn have to get smaller and smaller. And I would even say closer and closer to 0, right? So if they don't just continually get closer and closer to 0, then that means that the corresponding partial sums are jumping around by more. And that would prevent the series from converging. So let me go ahead and just state the divergence test. Okay, so let sum k equals 1 to infinity bk be a series. And then the series diverges if the limit as n goes to infinity of, okay, and I'll just be consistent with your book. Your book uses k here. This k goes to infinity of bk, right? And this, I guess this matches this index here. So if this is not equal to 0. And there's two different ways that this limit could be non-zero. So it diverges if the limit doesn't exist, and it diverges if the limit exists and is non-zero. So, okay, so given that statement, then we've actually gone through and we've seen that that the divergence test, so we've already done this one part here. So the limit as k goes to infinity of k over k plus 1, this is equal to 1. So by the divergence test, this series diverges. Okay, I want to do one other example for you, and then I will pause and let you do these other 3 examples. And I think I had meant to put this example right here, but I will go ahead and just comment. We've already shown that the harmonic series diverges. Okay, so let's look at the series, the harmonic series. And if you're we just showed that it diverges, right? the limit as k goes to infinity, 1 over k. And so this is going to be a caution. Okay, so the limit as k goes to infinity of 1 over k is equal to 0, right? And so the point is that we know, so the divergence test can only detect divergence or be inconclusive, right? So let me put my caution in red. If the limit as k goes to infinity of bk is equal to 0, the divergence test is inconclusive. Right? So, so this series diverges. And so I just want you to keep this in mind. So if you have, so it's usually very easy though to take the limit of the terms of a series, and so it's a good quick check. If the terms are not going to 0, then the series definitely diverges. If the terms are going to 0, then you need to do a little more work to investigate the series. So, okay, so I'm going to go ahead and stop this here and let you work the last 3 of these problems here. So these 3, investigate what the divergence test says about each of these 3 remaining series here. Okay.